who discovered that Earth is round? No single voyager or genius flipped a switch. Sphericity emerged from many minds across centuries, then was demonstrated beyond doubt when ships returned from the opposite horizon. Early cultures pictured flat disks, domes, or layered worlds, but sailing and skywatching raised a harder question. Why do new stars rise as you travel? And why does a ship's hull vanish before its mast? Practical observation began to erode flat world models long before telescopes. Classical thinkers stacked empirical clues. Lunar eclipses always showed Earth's round shadow. Travelers saw unfamiliar constellations as they changed latitude. Ships dipped below the horizon hull first. These repeatable patterns suggested a curved surface, not a boundless plane. Accepting round wasn't enough. The next leap was scale. By comparing the sun's angle at two cities at the same time on the same day, ancient mathematicians could compute Earth's circumference with striking accuracy, turning a philosophical claim into a measured fact. Centuries later, oceanic expeditions closed the loop. A crew that keeps sailing generally west and returns home without magic or edges offers a public, practical demonstration that any skeptic can grasp. The route works only on a world that curves back on itself. This opening establishes the core: evidence, measurement, and demonstration. Next sections will trace the timeline: who proposed, who argued with observations, who measured, who navigated, and how the idea survived through empires, religions, and renaissances. No, medieval scholars did not universally believe in a flat Earth. Educated traditions preserved the spherical model. No, one sailor proving it isn't the discovery. The voyage confirmed what scholars and navigators already used. No, pictures from space are not the first proof. They are the latest confirmation in a very long chain. The round Earth wasn't discovered once. It was discovered better. Next, Section 2. Early philosophers and observers who first assembled the case, from aesthetic hunches to eclipse shadows and changing stars. Long before anyone sailed around the world, observers stacked simple clues into a powerful argument. The round Earth was not a guess. It was a conclusion from everyday phenomena anyone could check. Watch a vessel sail away. The hull disappears first, then the masts, as if sliding behind a curve. Reverse the scene from a watchtower, and the ship rises mast first. On a flat plane, distance makes things uniformly smaller. It doesn't hide bottoms before tops. Travel north, and familiar southern stars sink below the horizon, while northern ones climb higher. Go south, and the Southern Cross rises. The sky changes with latitude in a way that fits a curved surface with different windows on the celestial sphere. During a lunar eclipse, Earth's shadow bites a dark curve across the moon, and it's curved no matter where the eclipse is seen. Only a round object always casts a round shadow from every angle. A disk or slab would sometimes cast an ellipse or line. Drop stones in all directions, and they fall toward a center, piling to minimize height differences. Philosophers argued that, left to itself, matter, seeking a common center, forms a sphere, the unique shape with all points on the surface equally distant from the center. Some early thinkers admired the sphere as a perfect form, but admiration wasn't proof. What convinced scholars was the convergence of independent signs: horizons, stars, shadows, and centers seeking weight, each consistent with the sphere and awkward for a flat world. By the classical age, pilots and traders used latitude clues from star heights to guide travel. Practical guides tacitly assumed curvature. Predictable star shifts with north-south distance become a tool only if Earth is round. Premise 1. Ships vanish hull first behind the sea's curve. Premise 2. Star fields change predictably with latitude. Premise 3. Earth's shadow on the moon is always round. Taken together, they imply a spherical surface sharing one center. An elegant, testable model. Arguments establish shape. Measurement proves scale. Next, Section 3. Measuring the world without leaving home. How comparing sun angles at two cities turned Earth is round into a number anyone could calculate. Arguments say it's round, but measurement says how round. This section shows how ancient observers turned shadows and star heights into Earth's first circumference numbers, no ship circling the globe required. If the sun is very far away, its rays are effectively parallel at Earth. On the summer solstice, at noon, the sun stands straight overhead at Syene, near modern Aswan, casting no shadow down a vertical shaft. At the same moment in Alexandria, a vertical stick casts a measurable shadow. The shadow angle in Alexandria is about 1/50th of a full circle, about 7.2 degrees. If the north-south distance between the two cities is 1/50th of Earth's full circle, multiply that distance by 50 to get the planet's circumference. Surveyors paced or otherwise estimated the distance between the two cities, about 5,000 stadia in ancient units. Multiply by 50 and convert stadia to modern meters, and the result lands remarkably close to today's values for Earth size. Despite small assumptions, the cities aren't perfectly on one meridian, Syene isn't exactly on the tropic. Simple geometry links arc angle to arc length on a circle. Parallel solar rays mean the measured shadow angle equals the central angle between the two locations. A single noon snapshot avoids daily solar motion complications. Picking the solstice maximizes contrast at low latitudes. Another path used a star Canopus. Note its elevation above the horizon in Alexandria, and that it skims or sits below the horizon farther north. The change in the star's elevation corresponds to a slice of Earth's circumference. Combine that angle with the overland distance to estimate the full circle. Different distance assumptions yielded differing results, showing the method's sensitivity to baseline accuracy. Angle accuracy was excellent. Distance was the weak link. Even with imperfect baselines and unit conversions, results clustered close to modern values, evidence that the spherical model plus careful observation gives predictive power, not just philosophy. Later centuries refined distances with triangulation networks and much later, satellite geodesy. Yet the logic stayed the same, linked known angles and baselines to recover Earth's size and shape. What began with sticks, wells, and stars evolved into a precise science without changing the core idea. A number makes maps honest. Knowing Earth's scale lets cartographers fix how far coasts really lie, helps navigators budget food and water for voyages, and anchors long-distance trade routes to reality rather than rumor. By turning shadows and star heights into miles, ancient scholars proved more than shape. They proved scale. Next, Section 4, Keeping and Transmitting the Round Earth, how the idea survived through Roman, Islamic, and medieval scholarship into charts that guided the age of exploration. Once Earth's sphericity was argued and measured, the challenge shifted from discovery to preservation, copying, teaching, refining, and applying the model through empires, languages, and changing institutions. Geographers and encyclopedists folded Greek astronomy into practical learning, latitude by star heights, climate zones, and curved Earth cartography. Copyists kept mathematical texts moving through libraries and monastic scriptoria, so pilots and scholars still had spherical assumptions baked into tables. From the 8th to 10th centuries, scholars sponsored large-scale translations of Greek astronomy and mathematics into Arabic, then critiqued and extended them. Star catalogs, astronomical tables, and instruments, astrolabes, quadrants, were recalculated and localized, reaffirming a spherical Earth as the working canvas for navigation, prayer time-finding, and geography. Equal-hour sundials, astrolabes, and terrestrial and armillary globes all assume curvature. They only work consistently on a sphere. Observatories compared theory to sky positions, tuned tables, and taught generations of students who carried spherical methods into surveying, timekeeping, and map-making. Philosophical discussions about Earth's motion or scriptural readings did not erase the spherical baseline for practical astronomy. Where disagreements arose, computational astronomy and geodesy kept using spherical geometry because it predicted eclipses, star risings, and travel latitudes with reliable accuracy. Arabic to Latin translations of Ptolemy and commentaries reseeded universities with spherical cosmology, trigonometry, and instruments. Texts on the celestial sphere, eclipses, and climates became core curriculum, equipping pilots and map makers across the Mediterranean and Atlantic frontiers. Terrestrial and celestial globes, portolan charts, and latitude sailing practices operationalized curvature. Pilots targeted parallels, corrected declination, and expected horizon effects. Mariners didn't believe in a sphere on faith. They sailed inside its geometry. It unified sky and sea in one model. It compressed diverse observations into a single testable framework. It linked to tools that worked the same way from court to quay. The same stars, the same angles, the same results. By the time oceanic empires launched, the round Earth was not a speculation, but the water they swam in, embedded in tables, charts, and instruments. Next, Section 5. Public proof at planetary scale. Circumnavigation, better geodesy, and why round became oblate as measurements sharpened. By the time blue water empires set sail, scholars already worked with a spherical Earth. What followed made it undeniable to the public, and then refined round into round but flattened at the poles. A ship that keeps a general course and returns to its starting port without turning back makes a practical, public case for a curved world. Crews track changing star heights, shifting magnetic declination, and date offsets across time zones, signatures that only make sense on a globe. Ocean routes exposed map errors and forced corrections. As long-range voyages multiplied, chart makers calibrated coastlines with latitude observations, improving scale and coast-to-coast consistency. The more the oceans were crossed, the more sphere became lived experience. Better instruments raised a new question. Is Earth perfectly round? Precision pendulums and gravity measurements hinted that weight varies with latitude, and meridian surveys suggested the planet is slightly squashed, wider at the equator than pole to pole. Spinning pushes outward most at the equator, easing gravity's inward pull there, and letting the equatorial radius bulge. A self-gravitating, rotating world naturally relaxes into an oblate shape, the minimal energy configuration for a fluid or ductile body over geologic time. Triangulation arcs in different latitudes, precise star timings, and later satellite tracking pinned down the flattening and average size. The sphere matured into a mathematical ellipsoid, and then into an even subtler geoid that follows gravity's lumpy reality. Commercial flights follow great circle routes that curve on flat maps, but shorten real distance. Satellite dishes tilt differently by latitude. GPS and global communications rely on Earth's measured shape to place receivers and clocks where calculations say they are. Who discovered Earth is round? Many hands. Observers argued it from eclipses, horizons, and stars. Mathematicians measured its size. Sailors publicly demonstrated its curvature. Geodesists refined its exact figure. Discovery is a relay. Argue, measure, demonstrate, refine. The result is a world that's not just round, but precisely mapped, enough to steer ships, land aircraft, aim satellites, and synchronize clocks across a turning, slightly flattened Earth.